In today's video lesson, we will be covering the basics of measuring scientifically and using sig figs properly. To follow along with this video lesson, I would recommend watching this on either your computer or your phone so that way you can take notes on your iPad. So when we talk about measuring, there are different units or different things that we measure. So one thing we will measure is volume. Volume is going to be the amount of space, I'm sorry, it's terrible handwriting, space occupied by an object. Good way to look at this is like when you buy a 2 liter of soda. The bottle has 2 liters of space in it, and then they can fill it with, about 2 liters of soda. So that is the volume, that is the space being taken up by that 2 liter of soda. When we talk about length, that is going to be the distance between 2 points. So if we wanted to measure, the length of our iPad or the length of this line, we would measure the distance between the point here and the point here. Mass is the amount of matter in an object. One thing that I do like to remind students is that mass and weight are not the same. We'll get more into this when we get to the physics portion of the class, but mass has to do with how much matter or what an object is made up of, whereas weight is actually affected by gravity. So anywhere you go, whether it's here, the moon, Pluto, anywhere, your mass is the same. However, because gravity changes, your weight would change. But again, we'll get more into that when we get to the physics portion of this class. Time, well, realistically that is just the time between two events. And then temperature is the measure of the energy that particles have. So particles, like the air around you, is made up of atoms and molecules that are moving very, very, very fast. While when something is hotter, those molecules are going even faster. When something's cold, those molecules are moving at a slower speed. And when you take the temperature of something, that's what's happening, is it is measuring essentially how fast those molecules are traveling. Significant figures are definitely students' favorite thing that we're going to learn this year. Significant figures are how we properly measure using any given device scientifically, or how to scientifically measure. So significant figures are used to show the accuracy in a measurement. So accuracy depends on, and I would recommend highlighting this, accuracy depends on the smallest increment shown on a measuring tool. So that's like on a meter stick or a balance or anything like that. The last decimal place or digit for a number is considered to be an estimate. And this all probably seems a little confusing right now. It'll make more sense as we go through the slides. The more decimal places or digits, the more accurate of a measurement it is. For example, if I draw this line here, well, if I use one tool, and the last place, like we said, the last decimal place is considered to be an estimate. Well, if I said this line was 0.7 meters, but then using a more accurate tool, I was able to say it is 0.753 meters. Well, this is considered to be a more accurate measurement because I have more decimal places. Again, as we go through the notes, it'll start to make more sense. So with any tool that you have, you always want to try and figure out, well, what is the smallest increment on a measuring tool? And some of you are probably wondering, well, what is an increment? An increment is going to be the gradual increase from one place to the next. So like here we have the big numbers of 7 and 8 on this ruler. Well, our increments then are going to be these lines and what these lines represent. So like here, this first line would represent the number 7.1. This line would represent 7.2. This line 7.3, and so on. So what that's saying, or what you notice with that, is every time we move over one of those lines, we are increasing by 0.1 centimeters. So that means that our increments on this are going to be 0.1 centimeters, also known as tenths. because it is our tenths place that's increasing here. And if you look at this, you'll notice we went 7.1, 0.2, 0.3. Since it's our tenths place that is changing, this is going to mean our smallest increment is the tenths place. And this doesn't only apply to rulers. This will apply to graduated cylinders, triple beam balances, anything like that. Those are all tools that we're going to use in this class. And for any one of those, you always want to find your smallest increment. Now is one of the key parts of significant figures. So after you determine your decimal place, so in the last example, and I'm just going to draw x's just to represent any number. If we had like x point x, in the last slide we said, 7.1, 7.2, etc. Well, this number is our smallest increment, but what we actually want to measure to is one place value further, or the next decimal place after your smallest increment. That's the key point of any of this. So if I were to estimate this, the length of this pencil, we would look and see, alright, here's 8, here's 8.1, here's 8.2, and if I draw a line straight down from this pencil, I can see I'm falling somewhere between 8.2 and 8.3 centimeters. So that means my smallest increment, I have 8.2, and I know I'm between 8.3, so I want to estimate the next value place here. So I'm going to estimate straight down, I'm going to say 8.25 centimeters. So this is our increment, and you always, 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 no matter what, go one place value further. So always find your smallest increment and go one place value further to the right. So my next decimal place would now be to the hundredths place. Just as a quick refresher, if we talk about our placeholders, we have our ones place here. This is tenths, hundredths, thousandths, 10,000ths. Just as a quick refresher. So if you ever find something to have, a smallest increment of thousandths, you would estimate then to the 10,000ths. If something has a smallest increment of ones, you would estimate to the tenths. So you always just find your increment, go one place value further to the right. I would like you to now pause your video and try and measure this pencil to the correct value place. Okay, now that you have tried this on your own, looking at these answers, and I know we just basically did this on the last slide, if we draw straight down from here, something like that, you will get an answer, and if you estimate, you're probably like, okay, I can tell it's between 8.2, 8.3, so we're going to estimate our last value place to, and based on these answers, probably 8.24 or 24. Now, what some of you are probably wondering is, well, why isn't this a correct answer? Because it's still 8.24. But one thing you'll notice is this 0 here. And I would actually like you to pause the video again, take a minute, think through why this is not a correct answer, but this one is. If you struggle with this, I do understand it's a tough concept. But the reason being is this 0 here would mean that our smallest increment was the hundredths. Our smallest increment wasn't the hundredths. Our smallest increment was the tenths, which means we are estimating to the hundredths place. If our last number is the thousandths place, that means that our smallest increment had to be the hundredths. If we recorded this number with this ruler, that would mean that we were lying about the accuracy of our measuring device. Again, I know this is where it starts to get a little bit more challenging and confusing. I promise we'll keep practicing on this. But the rule is, the simplest way is always, always, always find your increment. No matter what it is, let's pretend it's to the tenths place. Your number always has to go to the hundredths. If your smallest increment is to the thousandths, you have to go to the 10,000ths place. This slide just goes on to explain a little bit how we measure. Since we know that right here is 8, this is 8.1, 8.2, 8.3. We can tell that the pencil is longer than 8.2. It was past this line, but it was shorter than 8.3, so it falls in between those two. And then the 0.4, a lot of students freak out and are like, oh no, what if I said 8.26 instead? Well, the last digit is just an estimate, so it doesn't have to be perfect. But if you look at the gray line here, it does look like it's closer to the 8.2 line than to the 8.3. So we're going to guess somewhere around 8.24 centimeters. So your last number is always an estimate. In this case, we have our 6 line here, but then 7's right here. So this is kind of a weird graduated cylinder. Since there's only 4 lines in between them, we know all of these divisions have to be the same. So if you break this into 5 segments, this would be 6.2, 6.4, 6.6, 6.8, and then 7. So if we keep following our rules for measuring properly, we can tell this line looks like it falls pretty close, or if you look at the top of this line, you can tell it looks like it falls pretty close right to that 6.6 line. Well, since this goes down to the 10th place technically, since we do have, our decimals in there of 6.8, 6.6, 6.4, 6.2, we do want to measure this one down to the hundredths. So this is going to become 6.6, and even if I think it is right on this 6.6 line, we have to still go to the hundredths place. So we would put that as 6.60. Now I would like you to please pause the video and try and measure the volume in this graduated cylinder on your own. Okay, now that you have tried to do this one, let's first go through and determine our increments. If this line right here is 50 and this line is 60, well, this line would then be 51, 52, 53, 54, and so on. And this is one that tricks students, is because a lot of times they're like, oh, well, we've been going by tenths this whole time. Not in this case. If this is 50, this first line's 51, then 52, and so on, you can tell that we are actually increasing our ones place in this case. So if we look what this is between, which would be lines 52 and 53 here, well, my smallest increment is the ones, which means I need to estimate to the tenths place. And looking at this, to me it looks like it's pretty close to this 53 line that's right here. So I might estimate this one to be 52.8. And so hopefully you pick number 3 as your answer. Now, if you picked number 4 for your answer, some of you are probably wondering, well, why isn't number 4 correct? Aren't 52.8 and 52.80 the same number? Not when it comes to measuring. And I will show you an example in the next slide as to why that doesn't work. The number, and the important thing to keep in mind with science, is the number that you report shows the accuracy of your device. So let's look at an example on the next slide. Alright, so here's an example where we have 3 different graduated cylinders. The one on the left has the smallest increment of just 1 liter. You'll notice there are no other lines running along the side here. Our smallest increment is just this 1 liter. So that means this is just going to the ones place, and if we measure properly, we would have to estimate this one down to the tenths. So if I were to estimate this one, I would guess, I don't know, maybe 0.7, like I can tell it's above the halfway point, which would be somewhere around here. I'm just going to guess that this would be somewhere around 0.7 liters. Okay, now if I look at the second graduated cylinder, well, this is a better one. I now have increments on here of tenths. So now if I look at this one and I were to estimate, I can see, okay, well, I'm clearly between 0.6 and 0.7. So I'm going to say my answer is somewhere around 0.6, and I'm going to guess maybe I'm a little over halfway, so we'll guess like 0.66 liters. And then if we look at this last one, and sorry I know this isn't perfectly drawn, but you can see in here we have even the tiny little increments on there. And so if this is 0.5, this must be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10, which means that each of these tiny ones, like right here, would be 0.51, 0.52, 0.53. And so if we go up and look at this line, well, I can see, okay, here's my 0.6 again, and I'll label that just to make it a little bit easier. Here's my 0.7. And if I count these, okay, well, this is 0.6, 0.61, 0.62, 0.63, 0.64, 0.65, 0.66, and now I can tell, okay, I am very, very clearly lying between 0.66 and 0.67 here. So now I feel more confident than I was before. So this is 0.66, and it looks like it's just barely above that 0.66 line, so I'm going to guess this one to be 0.63. So again, this one we have increments down to the hundredths, so I'm going to estimate my thousandths place. And going back to on the previous slide, discussing, well, what's the difference between each one of these? Why was that, I think on the last slide it was, why was 52.8 correct but not 52.80? Well, the reason being is this right here, this 0 would indicate that we were using a graduated cylinder going down to the tenths place. We would be lying to other scientists about the accuracy of our measurement. So if we look at the second one here, by me having this place, the hundredths, as my last place value here, I am telling people that I can for sure tell that my number is lying between 0.6 and 0.7 because those markings are on there. And so they know that my last place value was an estimate, but they can feel confident that the water measurement was between 0.6 and 0.7. They can't really feel confident of anything past that because that last number is an estimate. Or if I look at the third graduated cylinder here, I can tell for sure that not only am I between 0.6 and 0.7, I can tell I am between 0.66 and 0.67. So again, this last number is an estimate. So they can feel much more confident in the accuracy of my measurement using this third graduated cylinder. And that's why on the last slide, 52.80 is not correct. Because the graduated cylinder in that case was going by increments of 1, which means that the tenths place value was estimated. If they recorded 52.80, they would be lying about the accuracy of the device that they measured with. If this seems overly complicated to you, I understand. It's a weird concept, but just know, always find your smallest increment and go one place value further to the right. Alright, I would like you to please pause your video and try this one. Okay, so if we look at this one, notice that this one says it is in millimeters, so that's going to be our units. And if this is 10 right here, and this is 0, well, that must mean that this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so if we go through and look at this one, well, if our increments are increasing by the ones place, my answer has to go to the tenths. So we can't answer 8 for this one, we can't answer 8.00, and we can't answer 80. So right there, without even doing the measurement, we can go ahead and assume that 8.0 is our correct answer because it's the only one that goes to the proper sig fig, that goes to the proper place. And if we draw a line down here, we can see, okay, it's at 8. It looks like it would fall right on that 8 line. But my number that I record has to go to the tenths place, since my increments are increasing by 1. So therefore, my answer would be 8.0. I do need to have that 0 on there. Just 8 doesn't work. 8.00 doesn't work because then again, we're lying about the accuracy of our measurement. So we have to say 8.0 millimeters. Triple beam balances are where this gets to be trickier. So if we look at it, they kind of go in weird order. Here you have this mass that's moving by increments of 100. The one back here is moving by tens. And then this one is actually going from 1, or from 5 to 6, sorry. And then that means that this is 5.1, 5.2, 0.3, 0.4, 0.5, and so on. So if we record this number, since this is sitting on that 200, our number is going to be 200. We have this one moving, increasing by tens back there, so 260. This is our ones place, so that's going to be 5. And then, if we look at this one, this is 5.5, 5.6. Sorry, I'll use the laser here. 5.5, 5.6, 5.7. So I know I'm lying between 5.7, 5.8. So I'm going to guess this to be a little bit further past that. And I'm going to say 265.73, somewhere in there, I guess, based off the answers on the right, 0.2. And so our correct answer is number 4. Triple beam balances can be trickier, but one thing I want you to remember, not all triple beam balances are the same. This one we had to read to the hundredths place. Some of them will go to the thousandths. So don't just see a triple beam balance and be like, yes, I know I'm going to the hundredths place. Think of all the graduated cylinders we've seen. They don't all go to the same place value. Some of them increase by increments of 1, some of them have all the lines and increase by increments of tenths. Just like not all graduated cylinders are the same, not all triple beam balances are the same. So please always find that smallest increment and go one place value further to the right. Here's a conversion process for converting between degrees Celsius, degrees Kelvin, and degrees Fahrenheit. This is nothing that you need to worry too much about, but it is a good reference slide for you if you ever wanted to figure out, well, what is the temperature in Fahrenheit equal to in degrees Celsius? As always, if you need extra help, please make sure to visit the Moodle page and scroll to the bottom where there is extra support in case you are still confused, or go in and see your teacher. We would love to help you out.